de Nepal. Okay. Muchas gracias a todos. Bueno, pues nada. Entonces, Nepal, bueno, la verdad es que me une amistad personal con personas que están allí y cómo han quedado sus casas, y estamos organizando para el día 30, ya os avisaremos, una cena benéfica desde SIE por las víctimas de Nepal para ayudar a ONG SAR a llegar hasta las zonas afectadas. Bueno, dicho esto, voy a empezar con la presentación de la compañía. Bueno, nuestra compañía tiene 25 años, estamos en nuestro 25 aniversario. Estamos muy contentos de coincidir aquí con la presentación de CARLO. Y voy a hacer una presentación muy breve de lo que ha sido nuestra evolución. Bueno, en 1990 se crea Sistemas Informáticos Europeos y la marca CIE Computer. En el 94 la empresa se especializa en el tema de redes y comunicaciones. En el año 96 nos introducimos en los primeros sistemas abiertos, con plataformas todavía en 32 bits y las primeras versiones de SUSE. En 1998 se instala su primer sistema HPC. En el 2000 firmamos un acuerdo con D+D, con el CSIC, con el Instituto Roque Serrano, con Enrique Lomba. En el año 2006 CIE se convierte en el primer fabricante local de sistemas HPC en España. Y bueno, sigue nuestra trayectoria. En el 2008 CIE se especializa en entornos de HPC y plataformas de cálculo científico independientes. En el 2010 desarrollamos nuestro propio entorno de HPC basado en SUSE y en sistemas. En el 2012 desarrollamos un nuevo sistema operativo, NARDONE, basado en CentOS, un derivado de Red Hat. Es el momento también donde empezamos a incorporar muchos sistemas basados en plataformas de GPU. Es un cambio bastante importante a nivel tecnológico, porque supone pasar de la computación solo en CPU a pasar a la computación en GPU y todo lo que ello ha aportado en cuanto a velocidad. En el 2013 hacemos la primera instalación en extranjero en la Universidad de Addis Abeba, en Etiopía, para el departamento de química teórica. Y en el 2014 pues, nuestro sistema operativo se convierte en un referente nacional. Es un sistema todo basado ya en plataforma abierta, todo son herramientas open source que no exigen pagar más royalties ni elementos adicionales. Y en el 2015 pues, estamos abriendo nuevos proyectos en extranjero y en empresas privadas a través de la gente de informática del Corte Inglés, que están aquí representados, el profesor Javier. Y bueno, pues casos de éxito, bueno, pues estamos en un montón de universidades, centros del CSIC, algunas empresas privadas. Y bueno, algunos casos de éxito pues son el entorno MD, en Addis Abeba, la Universidad Autónoma de Barcelona, el entorno MD con CentOS 6.6. Estas son las últimas instalaciones. Esta es una de las que estamos más orgullosos, en el IRB, basado en entorno, hay una pequeña rata, nuestro es entorno Intel y en GPU con la NARDONE 6.6. y todo con sistema abierto. Es una solución que tiene en total 60 GPUs y exactamente pues viene a aportar unos 300 teraflops de computación versus, por ejemplo, esta solución del IBIS, que también en plataforma Intel, pero basada en CPU, ¿no? O bueno, con Intel también, la Universidad de Computación de Madrid. Bien. Desde 1998 a hoy hemos ido pues, evolucionando. Como veis, cada vez los sistemas han ido siendo más densos. Pasamos de soluciones que eran en 4 U's a soluciones ahora muy, muy densas, tanto con GPU como sin GPU. Las soluciones son tremendamente densas. Tenéis ahí un par de soluciones en la carpeta que hemos incorporado como referencia y pues tenemos las mismas soluciones que en una misma máquina de 3 o 4 U's pues que ven hasta 4 u 8 GPUs en un mismo dispositivo. Bueno, estos son un poco todos los puntos donde tenemos instalados clúster, aparte de máquinas de cálculo que hay en muchos más sitios. Y bueno, esta es un poco la agenda para hoy. Bueno, yo he hecho un poco la presentación, vamos mejor de hora de lo que esperábamos. Bueno, ahora CARLO NARDONE empezará por la introducción, haremos una parada de coffee break sobre las 11, quizá un poquito antes, unos cuartos, y luego seguiremos con cuestiones de programación CUDA. CARLO va a hablar mucho, Alon speak. A la 1:30 tendremos la comida, luego seguiremos y a las 5:30 aproximadamente, quizá un poquito antes, abrimos un turno de preguntas para todos los que tengáis dudas y bueno, queráis comentar con Carlos cualquier tema. Bueno, pues muchas gracias a todos y ahora dejo a Carlos. This is your presentation and you can see the next.
Gracias, muchas gracias. Grazie. I think I have no Castellano at all, so I'm sorry for that. Maybe I potrei parlare italiano, but probably it's better to stay on to English. So again, thanks for your attendance. We will have a long day, I think, with lots of material. Clearly, this is an introductory course. There are lots and lots of details because to be introduced to have to program GPUs and take advantage of the acceleration given from GPUs. So I've tried to put together. I tried to put together several possible approaches. Mostly, since it's just one day, mostly the standard CUDA and OpenACC, the directives approach as well. We will have hands-on activities remotely through our nice labs based on Avatar cloud servers. So again, I hope that it will be useful. Just to start, I would like to have an idea about your background. So, how many people actually programmed or have access to source code for GPU cards? A couple of people, okay, 3 or 4, okay. I assume that all the others never touched any CUDA or other approaches, so this is, as I said, today it's an introductory course. On the other hand, I hope that some of the presentation, at least some, will be of interest also for people already accustomed to the programming and GPU programming. Maybe in general, how many people programmed parallel machines in general? Maybe with MPI or other stuff? More people, okay, good. Because this is good because I'll start relatively slowly on trying to put together the relationship between the evolution of parallel computers and processors and so on, and the actual GPUs. That's because, of course, GPUs are the latest object based on this concept of parallel computing. So I think it's interesting to have a sort of an historical and technological background for all the rest of the tutorial. So we start with this presentation. I'll try to put together, as I said, parallel GPU computing. I'll try to give you some ideas regarding the trends in the processor technology, why multi-core are important now. So I'll briefly describe the standard taxonomy of parallel computers, but now, and more importantly, I'll try to explain why GPU computing became so important in this HPC field. So in a slide, I would say this is the reason why parallel computing is effective. So the idea is to have many small piranhas, and in principle, if they are well coordinated, at least, if they don't go in those places, if they are sort of relatively coordinated, they can actually be more effective than a large fish, meaning a large, maybe multi-computer, multi-processor, traditional one. Okay. As you know, in the past we had just one core, one CPU inside a single processor, inside a single chip. Well, this is already sort of slightly outdated because it's typical to have nowadays on standard x86 processors to have this sort of numbers in terms of cores. But of course, as you know, the GPUs and the other accelerators are based on lots of cores, lots of relatively smaller cores. So we're talking about many core computing, many core processors. As I said, the parallel computing is quite relatively old, I would say. There are the typical, the well-known architect in this field was Cray, Seymour Cray, but even before Cray, we had several more or less research platforms, research computers, which were parallel in the 60s, even in the 60s. Those are mostly in the 70s, 80s, and so on. Basically, we have several eras in parallel computing. The vector ones, the vector machines, which in some way you can still consider as a parallel, because when you have a vector and you perform the same instruction on a vector, you have some sort of concurrence or parallelisms, okay? Then we had the era of massively parallel computers, for example, the connection machine, which is not here. My first parallel computer, the connection machine CM2. I wonder if anybody so old as me to remember that. No people remember this? Okay, at least two. Okay, the nice machine with the LED, you know, the red LEDs on the black cube. Okay. Cubes were hypercubes were very popular at that time. Of course, during the 90s and even in the 2000, we had the huge era of Linux clusters. So even today, we have Linux clusters, even though, of course, now we have Linux cluster, accelerated Linux clusters. Okay. Let's have a look at the technology of the processors. Okay. I think everybody knows Gordon Moore, simply because everybody quotes this Moore's law, which is not a law, of course, it's a sort of an empirical observation. Simply stated, it says that in, say, 1.5 years, 2 years' time, you double the number of processors on a single chip. This is very important because everything we see regarding the evolution of computing is based on this. Industry needs sort of needs to follow this rule, follow this law. So it's a sort of a self-fulfilling prophecy. This technological evolution, which is of course exponential, gives us so many things like sort of a supercomputer in our pocket, like smartphones. So everything which is related to the evolution of computer and informatics in general, it's thanks to this evolution. But maybe sometimes, most of the time, I would say, people quotes this rule in a bad way, simply because they say the performance doubles, which is not really true, as we will see. So first of all, it's interesting to see that in relationship with the Moore's law, but due to some other kind of scaling, which is too complicated to be explained now, the Dennard scaling, basically for lots and lots of years, we had a frequency improvement, with similar frequency improvement in terms of rate per year, okay? So up to, say, more or less 10 years ago, we had a sort of a free lunch. In other words, you have your source code, your application, you have your application. You simply wait for 1 year, 1 year and a half, maximum 2 years, and then your application simply double in performance. It's simply because the clock of your processor improved a lot. Okay, so this is a sort of free lunch. Even your sequential application was okay, after all, because of that. But as you see here, more or less 10 years ago, the industry hit a plateau. So basically, we cannot improve the frequency of our processor anymore. Okay. The reason what is the reason of this plateau? Is the fact that the power dissipation is now too large, because those Dennard scaling is not valid anymore. There are leakages and so on, things related to the technology of the gates on the silicon. So basically, we cannot go up to a certain limit in terms of power density. If you look at the figures for watts per square centimeter, you will see that modern processor cannot, well, if the frequency kept improving, we could achieve something impossible, like the same power density of a rocket. It's unbelievable. Okay. So basically, we stay in a safer limit, but still we have, of course, lots of important technological issues in terms of dissipation, so that now, well, future, even today, but especially in the future, we will have water cooling, this sort of fancy kind of things, especially in the larger, more denser supercomputers. And so, as I said, the actual performance trend reached a plateau. This is somewhat outdated, but still interesting to see lots of machines of different kinds. But the performance here is the relative to some VAX or reference machine, a mini computer, which is typically used for reference, historically at least. So as you can see, we have this plateau in performances for a single CPU. Okay. Another important point to be mentioned in the relationship between computing and actual results is the fact that computing alone is not enough, so to speak. You need to take data and read data and write data back when you're done. The point is that memory is improving in speed of access, but not at the same rate as the processor, at least up to the well-known plateau, as we said. So this gap must be filled with some tricks. Okay, that's the reason why we have so many cache levels, simply because we need to sort of hide the latency, the time of access, the latency between data from memory and the processor, which is able, of course, to make computations on those data. There are several possible architectures to hide this latency, and GPUs are very good at hiding latency in terms of throughput, as we will see. Okay. Another general concept which is important to understand in order to see whether your application is able to exploit more maybe the pure performance from the processor, and maybe some other characteristics such as typically the memory bandwidth, is something called arithmetic intensity. What does it mean? If I take, let's say, a floating point number, let's say 4 bytes, then, for example, suppose I'm doing simply a floating point operation like an addition or a multiplication. In this case, and then I take the result and go back to the memory. Now I'm doing something like just one float for each 4 bytes. So it's something very small in arithmetic intensity. This is a sort of flops per byte. So, well, on the other hand, if I'm doing, for example, an exponential on this floating point number, then I need to do many more actual calculations, because you have a series, as you know, you have to do some tricks in order to have this exponential with some approximate series and so on. So in this case, you have many flops per byte. So your arithmetic intensity is very large. Clearly, when your core kernel of your code is or your application is has lots of arithmetic intensity, and you are stressing some features of your processor or your machine, such as the pure performance, the peak performance. You are going on this axis. You are going to the peak performance, and this is typical of operations which in technical computing and scientific computing, HPC, is called dense matrix computations, for example, matrix-matrix multiplications. This is called, as I said, it's a very famous library called BLAS. This is +3 kind of operation. This is, as I said, very heavy in terms of arithmetic intensity. On the other hand of the spectrum, you have operations in which you perform few operations per on the data. For example, sparse matrix computation. Here you have lots of few data, and then you have to put together and do less calculation on top of that. So in this case, you are stressing the bandwidth to the memory, because you need you need a speed to the memory in order to get these bytes and have a few flops on them. As a consequence, your performance on your machine is not, it's limited by two things. This is not very well known typically. Typically, marketing people quotes something like a peak performance. Those are old machines, doesn't matter. It's a conceptual kind of point I want to mention. So the peak performance is something like a speed of light. You cannot go up beyond those flops in terms of speed of processor or processing. But not only do you have this limit, the peak performance, but you also have a limit in terms of bandwidth, which is typically seen as a sort of a line in this plot. A plot is a logarithmic plot of arithmetic intensity and gigaflops per second. So clearly, if your machine has got a huge bandwidth, you have this line is very, very steep. So, for example, this machine is very, clearly it's a vector machine, is much more powerful than a simple x86 processor. So the peak performance is higher, but also the bandwidth is much, much higher. Clearly, this should be much steeper, but we have a different kind of axis, so we cannot see that very well. And also because it's logarithmic, so you have a sort of a shift. Okay. So the important point, as I said, it's consider bandwidth together with peak performance, and of course, bandwidth is one of those nice things in CPUs. I'll go very quickly through the traditional taxonomy of parallel computers. This is because simply for historical reasons. For historical reasons, there is this thin taxonomy. So in principle, at least, if you have a single core, a single CPU, you have a single instruction, single data machine. There is an instruction pool, there is a stream of instructions taken and processed by the CPU. There is a data pool streaming through the CPU, which elaborates the data. Single instruction, single data. Clearly, as you know, as you probably know, the connection machine, for example, was something like a SIMD. There is this concept of a single instruction pool, the single stream of instructions, but each processing unit, in our case, could be a core, each processing unit process different data. So we are talking about single instruction, multiple data. In a way, inside the GPUs, we have a sort of SIMD, several SIMD units. So it's still a useful concept in a way. Also, consider that the vector instructions, which are inside your x86, nowadays they're called AMX, maybe, not sure. In any case, when you perform vector instructions explicitly, or with some tricks with the compiler, more or less it's some sort of a SIMD situation. This is another way to look at the same concept as a single stream of instructions, several data, so you have several different streams coming out. Again, this is sort of a void. Basically, no computer is based on this idea of having the same data with different instructions. It's a little bit weird. And of course, this is the more general kind of multi-computer, multiprocessor. Basically, any cluster is like this, or even any multi-core machine is actually like this. You have each processing unit, each core in your server, x86 server, is able to take its own data and perform different things, doing maybe multi-threading applications. So basically, most of the machines today are multiple instruction, multiple data. This is, again, historical. Nowadays, basically, we've got Linux cluster everywhere, or maybe custom clusters like Craze or Silicon Graphics. So SMP, just to remember those names, SMP stands for Symmetric or Shared Memory Processor. This concept is still valid in your single server. A single x86 server is a SMP machine, basically. So you have several processors, several cores. Each has got its own cache, and each can have access to a conceptually main memory, which is shared. So each processor can share the same memory and the same I/O system, even though maybe the architecture is more complicated than that, but in principle, at least, each core can have access to the same memory. So it's a shared memory kind of processing. As you know, a cluster is actually a distributed memory machine. So each node in your cluster has got its own memory, its own processors, its own I/O, and there is, of course, an interconnection network, which should be, of course, in HPC situation, you have, for example, InfiniBand, because you need speed and decent latency, specialized networking for HPC. Just to give, again, a quick idea of regarding the actual x86 architecture, historically, you have an Intel architecture which was based on this idea. You have a single or maybe two sockets in this case. Maybe you have several cores on the same socket. You had this concept of front-side bus, which was based on a single chipset, which was able to speak with the banks of memory, the DIMMs. And those DIMMs were accessible through this front-side bus to all the cores symmetrically. So you had this symmetric uniform memory architecture, of course, shared memory. In AMD, maybe something like 8 years ago, more or less, came out with this idea of having not having a front-side bus, so each socket has got its own memory controller with its own banks of memory. So you have, but still, through this specialized internal interconnect, which was called at that time hypertransport, you are still able to have access to all the memory. So it's still shared, but it's not uniform. It's a NUMA kind of architecture, non-uniform memory architecture. So, for example, this core was able to speak, to get data from this bank of memory through the memory controller, the hypertransport, can go here. So it is a non-uniform memory architecture. Nowadays, even Intel has got its own with a different name, QPI, but the concept is still that one. It's a non-uniform kind of architecture. At last, GPU computing. Okay. Up to now, it was only sort of setting the scene. By the way, you can have questions anytime, of course. So I wonder if everything was more or less clear. Was simply a sort of recap of the some of the things going on in parallel computing. So now let's see what happened with a few years ago. Let's say again more or less 10 years ago with GPUs. So one could say simply, well, GPU compute is nice because it accelerates my scientific and technical computations. It's of course, it's a sort of pragmatic way to see the things. If you look at the gigaflops per second peak performance, well, this is old, but just to give you the idea, single precision, double precision, in comparison with standard x86, you have a huge speed up, okay? And also even more in terms of bandwidth, gigabytes per second access to memory. And this is the trend in x86 main memory. This is the trend in terms of bandwidth to graphical memory, okay, GRAM. So one could say simply it's very fast, it's accelerated, but let's see why and what happened. Basically, the basic idea is the following. Standard CPUs are using the transistors given to us from Moore's law. They are using lots of transistors to optimize for low latency. So you want from a CPU, typically you want very quick computation and for a single thread. This is because the way processors were designed from the very beginning. A single thread must be very quick. So the CPU optimizes for low latency access. On the other hand, you have lots of levels of caches, lots of transistors inside the processor are devoted to typically level 2 cache, and then you have some level 1 cache inside the single core. Also, you have lots and lots of tricks in hardware in order to speed up this single thread. Typically, you have lots of control logic inside the hardware, so that you have something which is called the speculative execution. What does it mean? It means that many times the processor, the x86 processor and other standard CPUs are able to, they want to perform computations speculatively, even though they're not sure they will be used. This is sort of funny if you never know that, but it's something which must be done, and it can be seen from 20 years ago or even more, that it is very useful in practice. Several times, many times the branch is which you take in your instruction set, in your instruction stream, is taken. Some other time is not taken, but still it's very good to have this logic in order to speed up your computation. Other kind of speculative kind of things is like the hardware the control logic inside the processor is able to understand you're having access, for example, to a vector with some stride. So the control logic is able to calculate the stride, take the data before you actually have it, so and maybe perform already a computation. So it's very complicated. As a consequence, as a consequence, there are lots of transistors devoted to this kind of things. The out of order, for example, means that many times the hardware inside the processor simply changes the order of instructions in order to optimize. And then, of course, he has to reorder again, back again. GPUs are completely different, simply because they were graphical processors at the beginning. Graphical processors are optimized for data parallel throughput computation. Throughput means lots of different threads all together. Maybe each single thread is slower, of course, but all together they are much more effective. It's a difference between a jet fighter and one of those jumbo jet. In a way, it's the same difference. So GPUs has got lots of transistor actually devoted to computation, to the arithmetic logic. A little bit of level 2 cache as well nowadays, but not so much. And very simple logic, control logic, just enough, so to speak. So as a consequence, GPUs are more transistors dedicated to computation. The architecture is such that when you have so many threads, and those threads are quickly switched, you in a way you are hiding the latency. As maybe we will show this a little bit later. It's maybe too many concepts altogether, but the message is this one. Either CPUs for low latency and GPUs for high throughput. And so, why graphical processing came out with this optimization? Simply because, historically, again, graphics pipeline was designed like this. So you have lots of stages in order to process your data. You have to consider vertices in your 3D model. You have to get texture on your tessel. You have the geometry to consider in order to change your 3D model and so on. Yeah, there is the rasterization stage, the pixel stage finally. The pixel stage is something more closer to your display. But then you have maybe to blend because otherwise you have lots of bad kind of artifacts. So you have to blend those pixels when they are close in order to have a nicer view of your display. And very finally, at the end, you have a frame buffer, which is the graphical, in which a portion of the graphical memory, which is something like the actual content of your display. So at the very end, you have a display with lots of pixels, of course, after all those stages. Clearly, at the beginning of graphical processing for consumer market, so when NVIDIA started, basically, in the late 90s, all those things were basically hardwired into the chip, okay? But from very slowly at first, both from the programming side and from the hardware side, it was started to appear a concept called vertex programming. In other words, even from very late 90s, early 2000, programmers, graphical programmers, were able to write a small function different for each vertex, for example. So in a way, this graphical pipeline was starting to be programmable. So you have your graphical coding, and you could program each vertex differently. So this gives you lots of flexibility for your games. Typically, NVIDIA came out with games in the market of the games gave so many volumes in terms of selling cards. So basically, we're doing HPC because of gamers. So we have to thank them for this. starting from Doom. I think Doom was one of the first things which started this the NVIDIA sales. Okay. With the evolution of this idea, the latest architectures in the early 2000s started to be more flexible. So rather than having different kind of stages in terms of hardware, the designers of the chip came out with this idea of having a single kind of a unified graphical core, okay, and then through lots of stages, you simply change the code, the instruction inside the graphical core in order to implement different stages. So this idea gives you a more and more programmable way to perform graphics inside your graphical chip. On the other hand, we are talking about, when we were talking about programmable shaders and so on, we are talking about more or less this era, both in Windows platforms and basically Unix platforms. So the graphical programmer started actually programming vertices and then pixels and then shaders and so on. Very early, some weird researchers came out with this idea. Okay, we can program nice graphical instructions on this chip. Why we cannot do the same computations which are not graphical? This was called the GPGPU approach, general purpose GPU computing. At that time was something very difficult to do. So you need something like OpenGL strange instructions in order to maybe perform some matrix multiplication, which was completely unrelated to graphics, but was only maybe a CFD code or maybe simple code in that time. So this idea of having some technical computation on top of a graphical chip started on this era. And they came out with research kind of processing model for maybe the compiler and so on in order to translate those fancy language, parallel language after all, on top of maybe OpenGL or DirectX, so that actually you can actually have an executable on your graphical chip. Came out with several research papers and research approaches and so on. You still have you still can have a look at gpgpu.org site. It's one of the first ones who have lots of. It's a portal which gives you lots of news and papers and other stuff related to this idea. So finally, researcher, PhD student at I think Stanford, Jan Bach, came out with this CUDA model. And CUDA model was actually taken by NVIDIA, and now Jan Bach is actually our accelerated computing manager for inside NVIDIA. So the idea was actually quite valid. It was supported by NVIDIA, so that we have the GPU computing before CUDA era, but of course after that we have after CUDA era. Okay. So to summarize, why GPUs are attractive for HPC applications? Basically, you have at your hand you have a massively multi-threaded many-core processor. So it's something like having again a connection machine in a single chip. It's very similar to that. You have lots of gigaflops inside of on a single chip, especially on single at the beginning, but later, very soon actually, even double precision, which is important for many codes. High memory bandwidth. At the beginning, no error control and error correcting code, and now you have error correcting code, which is again important for computation. Of course, at the beginning, you don't need ECC for graphics. Why? Because if a single pixel is maybe black, it doesn't matter really, of course. But then, really, if you want to do some serious stuff, you need that. And then, as we will see, you have lots of programming languages built on top of maybe CUDA. Lots of programming tools to debug and profile your code and help you. And clearly, from the very beginning, those GPUs were used by lots of computational physicists, especially, and then from other fields. As I said, after CUDA era, you have an evolution from the hardware, the Tesla generation, Fermi, now Kepler, maybe even with ARM. CUDA at the beginning was basically only C, then started to get maybe Fortran, then the industry came out with a standard way to have this heterogeneous computing with acceleration called OpenCL. Then lots of improvements like, okay, even more now we are CUDA 7, so we will see later some details. So as a consequence, we had a growth in the adoption, as you probably know. So at the beginning, you had this kind of figures in terms of teraflops available, papers, teaching from university, and so on. Nowadays, we have a huge adoption in all kind of areas. Okay. So to summarize again, the concept is to have this concept of accelerated computing is based on this idea of having some sort of heterogeneity. Heterogeneous computing means you have a marriage. You have a marriage between the CPU, which is optimized for serial tasks, as we saw, and the acceleration from the GPU, because GPUs are optimized for parallel high throughput tasks. So we need to, in some way, to coordinate the two in some way. Architectures evolved. This was the first, as you can see. Doesn't matter the details, but just to give you an idea, the idea you have modules. You have modules in different modules. You have cores inside the module with maybe some specialized memory and some level 1 cache. Maybe you have a number of L2 caches in common with those modules. And you have at the end, you speak with the frame buffer, which is the graphical memory. Of course, at the beginning it was quite complicated for, the pipeline of instruction was much more complicated than today. Just keep it quickly, this is still the most important chip in terms of double precision, high performance computing capabilities. So it's a GK110 Kepler, which is based on a cleaner architecture. You have up to 15 modules. We call them streaming multiprocessor, enhanced. Up to 15, 7 billion transistors. There is a level 2 cache in common, unified. You have lots of lanes connecting to the frame buffer, so to the geographical memory, DDR5. Of course, you need sort of scheduling, specialized scheduling. We will see a few little more details later. And of course, you need to interact with the host through PCI Express. Inside a single module, you have lots of cores. You have 190, in this case, 192 single precision cores, 64 double precision cores, lots of additional units for specialized functions. You have 4 schedulers, so the so-called warp schedulers, we will see later. What does it mean? You have also some specialized memory for texture, constant memory, share memory, and so on. Some of those things we will see later. So as a consequence, as you know, GPUs are very effective in many, many areas in scientific computing. And so as a consequence, you have supercomputing sites like this one is in Lugano. I think it's still the largest European site based on GPUs. But not only supercomputers, but we also have supercomputing, parallel and GPU computing, even on smaller things which are useful in embedded situations. Like this is simply very similar to, conceptually speaking, to a Raspberry Pi, because it's an ARM, it's a system on a chip-based board, as a small board like this. So this system on a chip from NVIDIA, Tegra K1, is basically inside the same silicon. You have a quad-core ARM processor and a Kepler GPU. It's a small Kepler. You have only one streaming multiprocessor rather than 15, but still you have the same software stack, CUDA, whatever. So you can maybe program on your GeForce on your PC. You can program a nice code, and then you can transfer this code and compile on Kepler. You compile for ARM and have it for several applications like robotics, computer vision, and other fancy stuff. So in this supercomputing era, now we have the multi-computing. After vector and massively parallel, we have the multi-core, and many-core era. As you can see from, sorry, it's a little bit outdated, but as you can see from the top 500 list, of the top 500 supercomputing site, which is updated each 6 months, you have now, from this year going onwards, the total performance given from is basically given from GPUs. And in the future, we are still ongoing. So the US Department of Energy announced an important project towards exascale computing. So now we are going not only to petaflops. Now today we have more or less 10 petaflop machines, but we are going towards 2017 to something like hundreds of petaflops, so very close to exaflop machines, using IBM power processors and NVIDIA, the next generations of NVIDIA architecture called the Volta. But most importantly, those machines will achieve those performances thanks not only to the single process, but also because of this special interconnect between CPU and GPU. We are calling this NVLink. So, for example, in next generation, in a near time, next year, basically, we will have the Pascal architecture for GPUs, which will feature this NVLink interconnect between GPUs and processors, starting with power. x86 is not available for NVLink because, as you can see, as you may understand, it's difficult to speak with Intel. They have got their own interconnects, of course. So NVIDIA is playing with power, IBM power, open power actually, which is more than IBM, and in the future even ARM. Okay, so we will have this fast interconnect between GPUs, future GPUs and processors, not x86. But still, you can take advantage of a NVLink between GPUs. Another fancy technology which is important for such to give you not only pure peak performance in terms of processing, but also bandwidth performance, as we said. It's very important, the bandwidth. So we will have 3D chips for memory. So there's a stacked kind of memory. The chips are talking each other through interconnects directly through the silicon. So in order to have lots and lots of pins, we will not have pins, but direct silicon holes, so to speak, connecting electrically connecting all those stack of memory and the GPU as well through a silicon interposer. So there will be no soldering anymore, no pins, no soldering. Directly in the silicon plants, you will have this kind of stacked silicon module. It's really amazing. In this way, we will have higher, lots and lots of bandwidth and capacity, and energy efficiency as well. So the roadmap is basically this one. This is single precision floating point operation performance per watt. So for Tesla generation, Fermi, Kepler, Maxwell is the new one which is on single precision. So you can buy maybe a GeForce or a Quadro with a Maxwell architecture. The next double precision will be Pascal, and then the exaflop machine will be yet another generation. So I think we can actually just a couple of minutes so they can take a drop of water, and then we have more or less half an hour or so introduction to programming. I forgot to ask whether you can hear me at the very end. Okay. Even without microphones and so on. The acoustics is okay. So let's start again, because then we will have, after a break, we will have the CUDA session, but still we unfortunately still have some preliminary slides on GPU programming in general. So we basically we'll have a sort of a quick overview of on how you can program those GPUs, actually. So we have several approaches, multiple approaches, as it's written in the agenda. And so have a look, just have a look. So to go back to, again, the traditional parallel computing, parallel programming arena, it's funny to see that there are lots and lots of languages and frameworks and so on just for parallel computing, maybe too many. So there are lots and lots of fancy things. I took it from maybe, I don't remember, the guy covering all those names, or maybe Tim Matson, I think. Even during the 2000 time frame, still lots of, again, lots of approaches, languages and frameworks. Maybe the most important in the general informatics is bit threads, because bit threads is actually what any average computer programmer was typically using to program multiprocessors, multi-threading. But of course, as you know, in HPC, we have those huge two approaches. Some of you know already, but just to recap, in HPC at least, we have the approach for clusters, for distributed computing kind of architecture. So it is called MPI, Master Passing Interface. So in this way, you can have a standard way to program different nodes exchanging messages. That's why it's called message passing, of course. On the other hand, if you have a single server with shared memory, you can use OpenMP, which is a standard. Lots of compilers able to understand OpenMP. It's a directive-based approach. So you can program with directives some shared memory machine like x86 server. Very useful for nowadays that you have so many cores inside your server. They can interoperate, so you can have a hybrid code, and lots of research papers on this explaining that you have good performances. It's important to understand that the CUDA and other GPU accelerated computing models can interoperate with those two. Of course, with care. I mean, you need to know some details, but you can do that. So you can have hybrid parallel and distributed computing with the acceleration. Okay. So in the huge supercomputers, basically you need to do this, otherwise you don't get performances. You are not using your machine. So the basic idea of acceleration is this one. You have an application, your code. You isolate compute-intensive functions. You use the GPU to parallelize this function, and the rest of the code is still on the CPU, on the host. So you have acceleration by means of this split, so to speak. The split is done directly by the compiler, so you don't need to to handle the different executables and so on. For example, the NVIDIA compiler and VCC is able to do this for you. But still, you need to program this acceleration, as we will see. There are three main approaches, three main ways to accelerate your technical application. Libraries, directives, and in general, programming languages from CUDA to maybe MATLAB. Okay. Libraries, it's called drop-in acceleration. In other words, you don't care about CUDA or other things. You simply use an accelerated library. With directives, it's easier in a way, especially if you have a huge legacy code. You simply give hints to the compiler in order to accelerate some portions, maybe loops. And of course, in general, if you want really top performances, you need to really program CUDA maybe. Okay. Let's have a look at libraries. As we just said, it's the easiest way in some form. There is this drop-in approach, so You have other open source or free libraries, actually free accelerated libraries, or maybe commercial libraries to do that. It's important to understand that you don't not only have performances, but you also have tested, validated kind of functions. It's important, especially in numerical analysis, to have validation. It's taking effort to do that. Just consider NAG, for example, the NAG libraries, very used in scientific computing. Many scientists use NAG or other kind of similar numerical libraries simply because they're validated, they're well done, they're optimized, but also tested very heavily. So you don't need to do strange things to debug, and maybe there is some computational accuracy problem in your code and so on. So it's important the quality, and of course performance. Because it's, to be honest, it's to tune up to the last gigaflop your code. It's difficult even on processors. It's still an art on GPUs as well. So it's useful to have a library which is already optimized. So there are lots of libraries for terms of, especially with linear algebra, starting with linear algebra, but including also maybe pseudo-random numbers generators, signal processing like FFTs, MPP, as we will see a little bit, OpenCV, for example, for computer vision. Now many routines are accelerated. Neural networks, more recent one. We will see some of those inside those slides. This is yet another way to look at the same story. The NVIDIA ones are free and typically included in the CUDA toolkit. Some others are commercial. This is free, one version is free, another commercial. This is included in the CUDA toolkit. This is an example. Nowadays, GPUs, from a couple of years, researchers came out with a new generation of neural networks, very effective. They are called convolutional deep neural networks. And all the large internet providers are using that because of many reasons. But for example, Google, Facebook, Baidu, Microsoft, everybody is using those fancy deep neural networks in order to have computer vision analytics, and maybe speech analytics automatically from those neural networks. So they are everybody is using GPUs because they're very effective on, especially in convolutional neural networks in the training phase. As you maybe know, during training you need lots of computational power in order to train your neural network. When you have a trained net, then you can use it to predict, maybe on a smaller machine. Okay. So we came out with this library, optimized library, which speaks with the standard research framework for playing with those neural networks. One of those is called CAFE. And so if you are interested in this area, we can talk about this. Let's see in practice what you have to do when you want to use library acceleration. Suppose you have a simple, very simple multiplication with a vector multiplication plus another vector. SAXP is called plus terms. Basically, you substitute a library call with the equivalent in CUDA. Then you have to, in some way, to manage the data, because at least traditionally, the data is on the host, but you need data on the GPU as well. So we need to understand this. In the newer generation, this is not an issue anymore, but for didactical reasons, it's important to understand. Of course, then you recompile, including linking the library. So let's see inside the code. So this is the sequential code in calling this plus routine. So I'm performing a vector addition, multiplication and addition. Okay. So you add, you put the CUDA call, which is exactly the same. You need actually to initialize and close the library, because inside there are things related to the GPU. You need to, and this is important, you need to allocate vectors inside the GPU. This is because, at least, I guess I said, traditionally, there is a, and also physically, there is a difference between standard RAM, the host RAM, and the graphical RAM, okay? So you need to allocate, for example, a vector and elements, floating point, float, with some, this is wrong, but in any case, it's a trick in order to have a pointer pointing to the actual device vector. Device means GPU memories. You can call host, you can call the CPU the host, and the GPU we typically call device, okay? And then you need to transfer the data. So maybe you have, you prepare your vector or your matrix inside the host. You need to copy this data into the, you copy this data into the device memory explicitly. Now, today, you can do this implicitly without all those explicit transfer. But didactically speaking, it's important to understand that you have this transfer. Okay? And then, of course, you get the result back to your host vector. So there are lots of examples with performances. We cannot go through the details, but just to say that in terms of speed up, you are done. So, for example, this is a matrix dimension. You have, in terms of standard Intel optimized library, you have this kind of speed ups. Of course, up to a certain peak performance of your machine. The large, as every time in parallel computers, when you have more data, you have higher speed up. Higher the matrix dimension, higher is the speed up, and then you have a plateau. This is typical in parallel computing. The larger the data, more speed up you have. What's interesting to understand that with libraries now you can have also multi-GPU acceleration for free, so to speak. So this is an example of CUDA, the extended version. So it basically gives you, with the same interface, it gives you, if you have more cards or more GPUs inside your machine, inside your server, then for free you are using all those. One of the latest additions is also a solver library. Not only linear algebra, matrix multiplication, and so on, but also solvers. Now are included in CUDA 7, so there is no need anymore to go to some commercial solution. You have accelerated solvers with several kind of direct solvers and so on for sparse and direct and dense matrices. This is of course very important for lots of scientific codes. As I said, it's just a flavor of what's going on, so very quick. Let's have a look at the directives approach. So the directive approach is something like this. Sorry for the Fortran. I wonder if anybody is using Fortran?
Yes.
Oh, no. I'm a Fortran dinosaur myself, so actually it's a long time since I don't touch Fortran, but in any case. So basically you are putting hints to the compiler. They are called the directives, so they are sort of special comments, but the proper compiler is able to understand those and use those directives as hints. For example, in this case, you are saying between those loops, please compiler, those are probably CUDA kernels, I mean GPU kernels, parallel kind of computation. So please compiler, perform for me all these tricks, all the low-level details in order to accelerate only this. So as you can see, no CUDA, no data transfer and so on. It's sort of magic, but of course, as always, there are, when you really want to optimize, you still have to do something. And so we will see in the hands-on in the afternoon. OpenACC is a standard, NVIDIA Cray, Portman Group compiler, CAPS. Unfortunately, CAPS was a French compiler company coming from India, I think, but unfortunately they disappeared. And to be honest, Portman Group was bought by NVIDIA 1 year ago, so it's the situation now. But still, I mean, it's important that you have this optimized way to do directives for GPUs, and also in the future for CPUs as well, multi-core, and even Intel 5. So it's not anymore something like only GPU. So it's a standard, it's easy, it's open, you can have a look at the specifications and so on. It's a very targeting acceleration on accelerators in general, GPUs in particular, but accelerators in general. This is to be, it's a slightly different from what OpenMP is doing. OpenMP is including directives for accelerators. OpenMP is very old, as you have seen, as from the second half of the 90s. So it's very old kind of standard. Now with OpenMP 4, they started as a standard to have acceleration directives. A little bit awkward, but so the compilers are still immature. But our feeling is that in the future we will have some sort of convergence between OpenACC, which is only for accelerators, and OpenMP, which is very general because includes multi-core and now accelerators. Okay. So if you want to basically to accelerate your legacy code with directives, you can use today OpenACC, but be assured that you will have this path towards a larger kind of standard. Let's see what we can do. Again, Fortran 90 Fortran group. We will see what does it mean. Another larger example. So here we have we will do that in the hands-on. So just to give you a flavor. So okay, you tell the compiler, please accelerate this portion, but you can also say Please note that you have you need to perform some copy of data from the host to basically to the GPU. Okay. So you can have a quick. The good point of directive is the fact that very quickly you have speed up. Some speed up from when comparison with the CPU only. So you have a single code. Your standard code on CPU is now accelerated just with some directives. And of course, you have a single code. So if you give your same code to a standard compiler, it's the same. Okay. There are also other interesting, more recent example on actual large legacy code like Cosmo. It's a weather forecast large code from Europe, from a European consortium. And actually, you have real life speed ups. Even though, to be honest, it's very complicated, lots of modules. So maybe they started with some of those modules, but they can do that in some way incrementally. So it's a good way. With directives, you can have incremental speed ups in terms of your programming effort. Okay, so you can basically, now, another point to mention, Portal Group is still a separated business, so you can have basically a demo license for, I don't remember whether it's 15 days or more. The point is that inside NVIDIA, of course, we are pushing to have those compilers, the OpenACC compiler, for free inside the toolkit. I don't know when this will be available, but of course, it would be nice to have for all NVIDIA customers. I think we will have it in sometime in the future. Programming languages, of course, there are lots of possibilities starting from CUDA C, but Fortran CUDA, OpenACC for Fortran. You have of course, the higher level kind of specialized languages like MATLAB. Even Mathematica is so accelerated nowadays. You can play with C++. Lots of codes, numerical codes are nowadays C++ based. I wonder if how many people use C++? Some, good. Our example today will be based on pure C. I'm not a C++ guy because I'm a Fortranist. So, but it's important to know that the support for C++ is improved a lot on CUDA. So you have lots and lots of C++ 11 features which are supported in your GPU kernel code. Even Python can be of interest for many researchers. Let's see start from Windows. So again, to give a flavor of what's going on, have a look. We are looking at some very, very simple routine C, again the Saxby, and you can, and actually we will play in the hands-on with the CUDA, explicit CUDA C. So there are many small variations. We will explain this in detail. C++, it's again, as I said, it's supported, more and more supported, and so you will, you may have a template kind of things with for GPUs. So, but even more complicated than that. You have inside your CUDA toolkit a special kind of STL, which we call Thrust. It's very similar to STL, but it's targeting objects inside the GPU. So you can have in a very C++ oriented way. You can play with those objects, vectors, for example. You can copy, sort, and have computations on top of that. Very simple kind of things, but it's very C++ oriented. If you like STL approach for loops, for example, and handling vectors and objects, you can use Trust. Fortran, good point, coming from EGI. And other things like Python. So, as I said, there is an evolution of CUDA features, libraries, developer tools, programming languages. Some of those things we will see. Of course, we cannot cover everything. From CUDA 5 to CUDA 6 and nowadays CUDA 7, you have those things. We don't have very much time to explain things like IRQ. We will talk a little bit about multi-GPU, but very little. So, okay, so that's the situation. Again, a quick way to say, we will go very quickly because now we are probably fed up with this, but so library, CUDA C, Trust C++. You can have a simple, you can put with Trust, you can put a transform, put in your, how do you call it in C++, this construct, a functor or what? In any case, you have a sort of a macro inside your call explaining what you're saying with your objects. Fortran, even Python. There are special kind of Python do this. Of course, all the compile chain is able to do this because it's based on an open source compiler infrastructure. Now it's LLVM. Our CUDA compiler is based on LLVM. In more recent improvements. So traditionally, as I told you few minutes ago, you had this concept of system memory, host memory, GPU memory, accelerator. Basically, you have to transfer explicitly through those codes and so on. Actually, from CUDA 6, you have something which we call unified memory. In the unified memory, basically you can, a pointer here, it's understood by the compiler, whether it's host based on GPU based. So it's you can pass around pointers to some sort of unified memory space. Of course, pay attention because physically speaking, those are things still physically separated. So the compiler has to do all the deep copies when needed. But the nice thing is that you can basically perform a single allocation, and then the compiler must do the low-level kind of things to actually have the transfer. Okay. This is very important to have a cleaner code. On the other hand, so and especially when you have legacy code and so on, it's important. And also with the future architectures, with NVLink, we will have a sort of a better hardware to support this concept of unified memory. So it's a simpler programming model, simpler code porting, the single pointer we have said. Of course, you still have to understand the data locality, so maybe you want to do some hand tuning. It's still compatible with all these hand tuning kind of things. So rather than having, so basically you can have a single kind of malloc. This pointer is now unified. You call the kernel with this unified data. Of course, you need to still to synchronize, but we will see with the hands-on, especially, we will see what does it mean. Tools, there are lots of tools, command line and visual. We will have a small look. We will have some look at the visual profiler. Very useful because it gives you lots of suggestions, both on Insight in Visual Studio and on Eclipse for Linux. Even remotely, you can do debugging and so on and support. Nowadays, those tools are supporting remote hosts. Let's go quickly here. Okay, so in general, in the future, our NVIDIA idea is to support better this heterogeneous computing, so that in the past you have this hybrid program, and basically you need to take care very carefully about this hybrid situation. But in the future, with unified memory and other features, basically we want to achieve the goal of having a single program, a single code, which is then targeted by the compilers to the host and the GPU. So we will take advantage of the fact that many languages are including some parallel statements, like C++ for the future, C++ 17, I think it's called. There are some working draft suggesting that we should have directly in C++ parallel kind of instruction, like for each. Another nice point I forgot to mention is that not only you have a parallel partner group OpenACC, but they are coming with some support for OpenACC directly inside GCC. I don't know when this will be really actually available, but should be this year. Python, if you like it, you have this company giving you optimized Python. It's optimized even on a CPU, but it's also accelerated. There is again a free version and a commercial version. Some people is playing with Hadoop as well on GPUs. Still not know much about this. Java, again, I'm not an expert at all on Java, but especially IBM would like to push for that, because with this idea of having IBM Power and NVIDIA acceleration, IBM really would like to have more general applications, even in the enterprise kind of arena. They want to have them accelerated, so especially Java it's important. And finally, MATLAB, for example, and I think most of you know at least what MATLAB is. And this is a little bit old, but basically you have MATLAB accelerated directly inside the functions or specialized toolboxes. You need to buy parallel computing toolboxes, I think it's called, to have access to these accelerations, some of those accelerations. Or maybe you need to use a special statement in order to have element by element computations which are then accelerated onto the GPU. Finally, the last things for this general presentation, resources. Apart from the online resources on developer NVIDIA.com CUDA, there is also a nice MOOC on Udacity about GPU programming. Probably some of you know that it's this online open course trend. And on Udacity there is a free course of GPU programming. Very good. It's a very good one. And with traditional books, traditional paper and e-books, there are those ones are probably the most important ones. In order of complexity, so CUDA, by example, is very simple. You have simple things like vectors and so on, and then improving, but very step by step. So it may be too simple for you after this tutorial. This is more general. It's more it's an introductory. It's an very good introductory manual covering hardware and software, coming from NVIDIA guy. Another large manual more on developing, and then there is the huge book, Bible book with all the details, the CUDA book. I have it here. So with this, I think we have we can have a coffee break if you want.
De presentación de Carlo sobre un evento que estamos organizando y ya luego os dejo con Carlo, ¿vale?
Okay. Thank you everybody, thank you for coming. I'm David Ramirez, I'm data manager from CIE, and I only need 3 minutes, right? We are interested in the next year do a new meeting, right? Principally, meeting for administrator and technical user on HPC. There is a first HPC big meeting in Madrid, okay? This is to administration and development. And the case, we are very interested in do, for example, very routable, real case, comparison, and I hope to see you the next year, right? If you are interested, do a speaker, okay? You can contact with us in this mail address. It's so, right? Now, lo voy a decir en español, que se va bastante mejor. Mayormente lo que estamos buscando para el año que viene, ¿vale? Es hacer pues igualmente un nuevo evento, pero que sea un poquito diferente de lo que solemos estar acostumbrados. Me gustaría contar, pues, sobre todo con vuestros casos, vuestras experiencias y debatirlas. Ejemplos reales, pues un poquito, un ejemplo que se me viene a la cabeza, ¿no? Ahora con la reciente salida de Red Hat y CentOS 7, ¿no? Pues yo, por ejemplo, sigo utilizando CentOS 6. ¿Por qué sigo utilizando CentOS 6 y no me he pasado a CentOS 7? ¿O por qué tú te has pasado a CentOS 7 y has dejado CentOS 6? Yo utilizo Ubuntu, yo utilizo Windows. ¿Por qué utilizas Windows? Es un poquito, sobre todo, que esté destinado a lo que son roundtables, ¿de acuerdo? Que cada uno cuente su experiencia, que cuente su opinión. Ejemplos reales, ¿vale? De configuración de clúster, de máquinas de cálculo, manejo del mismo. Pues, por ejemplo, en las encuestas que tenéis hay pues una serie de ejemplos que yo he pensado que sería bien tratarlos. Si os agradecería que pusieseis, ¿no? Pues ideas que os pudieran ocurrir para dicho evento. Y lo dicho, que interesados en ser speaker, en participar, en colaborar, podéis bien enviarnos un correo a esta dirección de email. Y toda la información estará publicada puntualmente tanto en nuestra dirección de Twitter, @hpcsie, como en nuestra página web, ¿vale? www.sie.es. Y hablé, eso es todo, ¿ok? Carlo?
Now we have the problem with the connection, right?
Right, okay.
So, since we have...
okay, I'm going to stop the transmission.
It's a static kind of explanation. I'm very sorry because with playing around, it's very. I think it's very useful. Let's see if in the afternoon we can do something about this. So, CUDA stands for Common Unified Device Architecture, a fancy name due for historical reason, basically. So, as you have seen in the earlier slides, so you have you can actually put together many higher level kind of things on top of the compiler infrastructure. The CUDA evolution we have already seen. Let's go to the two different kind of sorry main models: the computing model and a memory model. Okay, let's start with the computing model. So you know already you have the host, you have the GPU, you have a PCI bus, PCI Express 3 now. So you have to traditionally, conceptually, you have to transfer data, copy data to the memory, GPU memory. The host loads a program, a kernel, inside the GPU. This is because GPU no operating system, which is good because the operating system is a burden, so in contrast with maybe Intel 5, they have this concept of having everything inside, even Linux. So it's a different kind of approach. It's a lightweight kind of thing. Of course, you need the host to load the program. This is again yet another similarity with connection machine. If you remember connection machine, you had the Sun Spark host, and you load those host was loading executable on top of the computing nodes, parallel computing nodes. And of course you play with the data and then you go back. Okay. So a portion of parallel execution is called CUDA kernel. The entire GPU can execute several kernels, maybe together, maybe in concurrency, with some concurrency, okay, with some overlaps. Conceptually, to start easily, let's say there is one kernel. Inside this kernel, you launch many threads. It's very fine-grained. It's completely different from what you say, what you do in MPI, where each MPI process is very, generally speaking, is very coarse-grained. Here, you have a fine-grained parallelism. You have lots of threads, many more threads than cores available. Okay, the CUDA threads are very lightweight, so the context switching is very fast, and so you can have even millions of those threads all together inside the GPU. This is very important to understand because at the beginning it's a little bit tricky. You can you are even you really need more threads than GPU cores in general. This is because with this context switching, if you have many threads, hide the latency of each singular thread, performing all those processing on different threads. At the end of the day, a kernel can be seen as a function. As a function executed on a device. So, a kernel is a sort of array of threads. Those threads are organized into arrays, executing in parallel. All threads execute the same code, so it's a sort of SIMD. You remember this morning. single instruction, multiple data. Actually, single instruction, multiple threads. Well, it's very similar. Each thread has a label, an ID, a label, so that you can, from this label, you can select the data according to the label. We will see quickly what does it mean. So you can control according to the label. So you have threads like this. You have maybe some, some array depending on this label. You can perform functions and so on, like C, standard C. And maybe the output depends on the label, okay? So in this way, you can in parallel process a very large array. So the key idea is you have to write a single thread program, but this single thread program is parameterized in terms of thread label, thread ID. Very simple actually, because as we will see, you can most of the time you have simple indexes and you can use this relatively easily. So typically you use this thread ID to select some portion of the data to be processed and to make some control flow decisions. You need to launch then from the host, from the program launching the kernel, you need to launch many threads such that altogether, all those threads can process the entire data set. With an example, as always, with an example it's much easier than it looks. So, another concept now. So there are lots of threads, many millions of threads, okay? So clearly it's complicated to have simply a thread number. There is also another reason why we need to give organization to those threads. We'll see this later. So those threads are organized into blocks, set of threads, blocks. So we group those threads into separate blocks. Okay? As I said, this is done because you may have millions of threads, and also because inside blocks you can do something, while outside blocks you cannot. Then, when you have all those blocks, we call this situation, we call this a grid. But this is done because when you launch different kernels, you can launch different kernels from the host with different number of threads and number of blocks. So you can launch different grids. We call this situation a grid, but again, it's just a name. It's simply to say we have this number of threads per block with this number of blocks. So clearly we map this situation, which is completely abstract, so to speak. We map this onto a physical GPU, and this can be done, and this is done by the runtime support. The runtime support is able to map all those blocks inside the actual hardware, as we will see in a moment. Now, many parallel kernels are embarrassingly parallel. In other words, each thread has got its own data. It's everything needed, and so different threads don't need to communicate each other. This is called embarrassingly parallel situation. In many different kind of codes, you have this possibility, this situation, but of course, not everywhere, not every time. In many cases, you need some cooperation between threads. Okay. There are examples like CARLO region, when you have a domain decomposition kind of calculation, you have to exchange data in the CARLO region of the domains. In this case, you have some sort of cooperation. And other possible examples, like for example a sum, reduction sum, we will see later. So when you have a global sum, you need to cooperate between threads. Okay. So threads may need to cooperate to share results, to have access to some common memory, shared memory. This is done using a special kind of memory inside the GPU, and which is labeled in a special way inside CUDA code. Now the main point is you can cooperate, the threads can cooperate only within a block. So the real reason why you have blocks is because in this way you can share some data. Threads can share data only within a block. Then you have many blocks. Of course, you can still share data through global memory. This is always shared. The so-called global memory, which is the standard external graphical RAM of chip, this is still in common. Okay, but if you want to have a fast shared access to cooperate, then you can do that only within a block. Of course, this is permits scalability, because typically when you have too many processes or threads accessing the same shared data, you hit a scalability limit. So if you have this, in this way, you can have a balance between fast shared access and maybe relatively slower access to some off-chip common memory. There is another concept interesting in order to map your CUDA code with threads and blocks onto some real hardware. This is very old hardware, doesn't matter. The point is, suppose you have 12 blocks of threads in your CUDA kernel. So as you have seen from the animation, suppose you have a small GPU like Tegra K1 or a small one with just 2 modules. In practice, your CUDA real maps all those blocks inside the 2 available modules. And so in practice, you have in this hardware, very limited hardware, you have in practice at each time step, or at least a portion of the time window, you have your hardware is able to process 2 blocks in a parallel way. Your specific hardware, and so on and so on. But of course, if you change the chip, maybe a larger one, a more powerful one, then transparently, the runtime support maps your blocks inside more modules. Okay? So in this way, you have a faster processing for your the same kernel. The same kernel is performing faster simply because you have more modules to process your blocks, your thread blocks of threads. Clearly, you may have some load unbalancing, but this is part of parallel life. In parallel computers, you don't always have, it's difficult to have all the time a perfect load balancing. In practice, this can be tuned, maybe playing with the dimension, the size of your block, and so on, but this is for optimization. Yet another machine, the larger GPU, of course, with those 12 blocks, you may have 15 or something modules, the streaming multiprocessors, and then maybe some of those are idle. Again, doesn't matter really. You still have plenty of possibilities. For this particular kernel, you can play with the thread block size, or maybe the next kernel will maybe cover use of the modules. So you still have the speed up. Questions? As I said, with the real life experimentation, it's really easier than just on paper. It's a matter of being accustomed to this idea of threads and launching many threads. Now another concept. I'm sorry.
One question. The size of the block is something experimental. I mean, you should try different block size. I mean, to obtain the better speed up or no?
Yes. If you want to optimize, you can experiment with different block sizes. Yes. In terms of how many threads you launch per block. Yes, definitely. And of course, the profiler gives you suggestions, so you can actually play around. In the future, we plan to. There are already some research tools in order to have it automatic, so that you can have optimal, block size and so on. It's still experimental, but I guess that in terms of future easier capabilities for easier accelerated computing, we will incorporate those automatic tuning, auto-tuning kind of things. Nowadays, you have really to experiment, to be honest. Okay. Now there is another.
There are some general rules.
Yes, there are some general rules. We will see some of those a little bit slowly, because otherwise altogether. Yes, there are some rules. Rule of thumb. Yeah. The threads can be indexed in different ways. In 1D, in other words, you have conceptually speaking, threads inside your block are labeled like in a single vector. Okay, so it's a 1D index from 0 to n-1. Okay, but actually you can have it even in 2D. So you can have an x dimension, x direction, and y direction. So you have two indices labeling those threads. This can be useful if you have, for example, a grid, a real kind of 2D situation, for example, an image, natural, to map threads directly into your natural parallel space. That's why we are supporting those 2D. So, for example, you have a matrix, you can play around threads, subdividing your matrix within threads with two labels, x and y. Okay? You can even have 3D. So in 3D, okay, we have a cube. Sorry, I don't have the image for a cube, but you get the idea. So you have three labels for threads inside a block. On the other hand, blocks can be numbered similarly. In other words, we have seen 1D labeling for blocks. So blocks are organized like a single vector, actually. Or they can be organized in a 2D fashion. So you have a x and y index for a block. Clearly, each thread has got a thread ID and a block ID. Okay? This is because there is this two-level kind of parallelism, thread level and block level. Again, seems a little bit difficult, but in practice gives you lots of flexibility. Yes.
3D.
Sorry?
A 3D numbering for blocks?
No.
Why?
No, wait a second. No, sorry, I was wrong. I have to check. And then I'm a little bit I'm thinking about it. I have to check. Sorry about that. So to summarize, you have, with regarding to the computing model, you have a kernel executing as a grid of thread blocks. The host launches a kernel on the device. A block is a batch, a set of threads. Those threads inside a block can communicate through shared memory and also synchronization, local synchronization. Of course, each block has got a block ID, each thread has got a thread ID. How can you use this? Okay, this is again this idea of different grids and so on. Unfortunately, I think I have the example later. Still a little bit of details. This is more like optimization, but so now I'll tell you just for in advance, so to speak, because it's again an optimization issue. But in practice, in real life, and inside the hardware, each module inside the GPU, each streaming multiprocessor can launch 32 threads altogether. This is called a warp. It's a naming scheme just to say that please pay attention to the fact that those threads on the hardware are in terms of 32. So many, this is, as a consequence, typically, the number of threads inside the block should be a multiple of 32, simply because it's a hardware implementation. So the real module, the real hardware inside the GPU, you have many of them, but one of those, the streaming multiprocessor, is able to launch this warp altogether. So we will see later what does it mean for optimization. Memory. Of course, each thread, like on standard CPUs, on standard CPU cores, each thread has got not only its instruction stream, but also local, very, very small, but local memory just for this thread. This is called register. You have a limited number of registers, like in any kind of processor. So clearly, the hardware is able to switch between threads and using those registers. So this could be a limitation in terms of how many threads in practice, how many blocks you can launch together on a specific GPU according to how many registers there are. Again, this is optimization kind of issue, but of course it's a very fast kind of memory just for immediate computation. Then there is the local memory for the thread. In practice, it's level 1 caching. Then, as you remember, when you have a block, so you have each thread has got a register just for immediate computation, local memory just for stacking, like a stack of memory. Then all together, those threads inside the chip has got a shared memory, so they can have access to very fast on-chip shared memory, where you can read and write. Then, of course, as I said before, all blocks within your kernel can have access to the global off-chip memory. So it's slower. It's still very fast comparison to CPUs, but of course it's lower than on-chip memory.
This global memory you're talking about, is global memory inside the card or the RAM of the CPU?
This is inside the card, but it's off-chip. Inside the card, but off-chip. Of course, if you go through PCI Express, you go to the system RAM, the standard RAM, that is yet another kind of memory, of course. So, as I said, there is a shared memory portion of the chip. Actually, on each SM, there is a portion devoted to shared memory. Other things for optimization, there are other kind of memories inside the chip, depending on the architecture. This is a bit slow, so sorry, a little bit old. Like as hardware, doesn't matter, because simply to say that there is a special kind of memory. This is for graphical reasons, but still you can, in some cases, you can use it even for general computations, because this texture, so-called texture memory, is very useful when you have sort of filter computation of small matrices. In this case, you have a very fast memory with very fast specialized filter kind of operations inside the chip inside the chip, so it's very fast, and all threads can have access on the same block, can have access to those computations. Again, it's an advanced concept. Another advanced concept is a read-only memory, constant memory, which is a sort of constant, also called the constant cache. Again, it's on chip, can be useful, for example, when you have parameters where you don't want to have access all the time from global memory. You want to have it very close to the thread, to the computation, is constant, and so you may use it. So this is a summary of the different kind of memories. I think this is wrong. I think this is wrong. This is also wrong. It depends on, I think it's two of these. I have to check it, sorry. Let's see.
In the card specification, would you say, for instance, GPU, Tesla, whatever?
Yes.
12 gigabytes.
This is global memory.
Okay.
This is global memory.
Okay.
This is on the off chip. Okay. And you have to take care, because in some models like K80, for example, you have two GPUs on the same card having maybe 24 gigabytes, but actually this is split between two GPUs. Okay. So each GPU has got, for example, 12 gigabytes on the K80. So, but it's global memory on the same card, but off chip. Global memory. Then, of course, inside the GPU, you've got special. You can query your hardware to have all the details regarding how much shared memory per SM, how many SM, and so on. You can query in many ways to have the details of your chip. Let's have a look at the real expressions on CUDA C. So there are a few extensions to standard C language. So clearly, if you give your CUDA code in the hands of GCC, he complains, because you are using some special keywords. There are not so many, but of course you need to know. So you have special labels with double underscore to tell the CUDA compiler that you have a function which is actually a kernel So global means that you can call this kernel from the host, execute on the device. Then you have device, maybe. Device is even more device specific, because a device function is a kernel which you can call from the GPU itself, not from the host, and then of course executes on the GPU. So global means that you can.
Are you?
It's funny to hear yourself.
The live stream.
And then, okay, this is a default, so it doesn't. You don't need to put this, but maybe if you have a cleaner code, you can use it. The host means a function is a function. It's a host-only function. Then maybe the most important things we will have access to, and there was also a hands-on detailed example. We have shared. So this, you put this qualifier in front of a variable to tell the compiler that this array, for example, will be shared within a block, shared memory. Constant memory is the other one, and it's read-only. There are also built-in vector types. We can skip it. Now the other extensions, very important extension in order to have a CUDA code. First of all, we have how do you launch a kernel from the host? You use this special triple bracket syntax. It's a little bit funny, but simply means that in your host code, in the normal CPU code, you launch a GPU kernel with the name of the function and the number of parameters, okay, as always. But you define your grid. In other words, you define how many blocks, you define how many threads per block. So that's that is where you can play around. So it means simply how many blocks you have, or maybe what is your 2D structure for blocks. Let's put it simple. This is the number of blocks, and this is the number of threads per block. Sorry, it's a little bit misleading, because in general, if you have maybe a 2D or 3D situation, here you are defining the structure of your block, but it's still a number of blocks in total, which gives you a grid. And here you have how many threads, how the threads are organized within a block. So within a block you have number of threads. Within a grid you have number of blocks. So again, how many blocks you are launching, how many threads per block. See, in general, you have a DIM3, so you have a three-dimensional structure for block dimension, and which means how many threads per block on each direction. With DIM is how many blocks in each direction. And then you have, last but not least, you have this index. So you have a thread index. IDX means index. And you have a block index. We will see later synchronization. This can we skip now? Let's have a look at real code. Okay, sorry. Again, this will be hands-on, but still we can have a look at the code. Okay, so standard code, again, our Saxby. So you have a loop, for loop from I0 to n-1, indexing. So this loop is indexing vectors, okay? In CUDA, you have a kernel we are launching this kernel from the host, so it's a global kind of thing. It's a kernel. It's a parallel kernel. The parameters, as always, of course, you need every time you have a vector, you need to pass pointers. This is typical for C, of course. Now, your index, the equivalent of this loop index, you have to calculate yourself. It's very simple, actually. Suppose you have a single, since we have a vector, we have a 1D situation, okay? So you can, basically, your index is the thread ID along direction X. It's a 1D. It's a 1D situation, so you have to put this, okay? So you have a thread index. Of course, this thread index goes from 0 to n, but for any block. So in other words, if you put only this, you will have different blocks having a thread 0, for example, performing something. Of course, you need to introduce a higher level sort of indexing, because you have different blocks. So how do you do this? How do you achieve this? You simply have a block index, but of course you have to multiply by the number of threads per block. So this, for example, suppose you have 8 threads per block. Very small, it's stupid, but let's say. So this goes from 0 to 7. Here the number is 8. So clearly from block 0, the index goes from 0 to 7, okay? From block 1 multiplied by 8 is 8. So this is go to 0 to 7. So 8 plus 7 goes from 8 to 15. So in practice, you have an index going through an entire 1D vector. So now you can perform an indexing with this loop. Clearly, so suppose the n is very large. Suppose n is very large and you have calculated correctly and so on. But in order to be sure that you are not going beyond n, typically you put this kind of control. So the index must be less than the total number of elements in your vector, and you're done. You're launching lots of threads all together in different blocks. GPUs will perform calculations in parallel, and you're done on this very simple stack speed. To put all together, as I said, you have this. We have just seen this kind of code. In practice, we have this kind of blocks and threads within block. Now, what happens inside your host code? Inside your host code, suppose you are allocating those vectors on the fly. So you allocate host vectors with a standard malloc. You maybe initialize reading somewhere, whatever. You need, this is again didactical, because now you can do more different things as we have seen already. So typically, you have to allocate device memory explicitly. So there is a CUDA malloc, gives you a pointer with some. Of course, you need some size. You pass this pointer distance for device, so you have an object, a pointer to a device memory. You have to copy the vector from the host to the device. So this is typically done again historically. You have to add to specify. Please perform a memory copy from host to device. So from host to device, those are pointers. This gives you this copy from these different kinds of memories. Finally, you invoke a parallel SAXP kernel. Suppose you want to use 225 threads per block, which is a good number. So as a rule of thumb, let's start with 128 2056, because it's nicely divided by 32, but it's on the order of the hundreds per block. Then you have lots of blocks. Which block, typically, it's better to have this number. So how many blocks in total? You have n, it's very large. Suppose it's 1 million. And you have a very long vector. Otherwise, you don't need the GPUs, right? You have huge vectors or matrices. So the number of blocks, it's, okay, this is a trick in order to have the proper final numbers, so that the number of blocks is enough, but not more than that, but not less. So, and then you finally launch the kernel with this number of blocks and this number of threads per block. That's it. You copy the result back from device to host through this keyword, device to host. Again, using pointers. Questions? Okay. So launching a kernel, well, more or less we have already seen that. This is more general, because in general you can also not only have number of blocks, number of threads per block, but you can also specify the size of the shared memory, and also something called stream, CUDA stream, which is a way to overlap different kernels together. This is maybe in the afternoon. If we have time, we can just give you an idea of how you can use this CUDA streams in order to overlap different things like you know, memory, maybe different computations and so on. Some rule of thumb. Clearly, you need how many blocks you need? At least you have at least 1 block per SM. If you have it's better if you have many blocks. Why? Because if you have many blocks, it's okay with a small GPU, but it still can be still okay for a larger GPU, because you have maybe 15 SM. So you have at least, if you don't have 15 blocks, you are underusing your hardware. So it's good to have several blocks, maybe a number of blocks per SM, but pay attention, and this is important to have scalability for future GPUs. But of course, if you have too many blocks, then you may get into some other issues, but okay, for the moment, let's keep it simple. How many threads? Okay. Okay, this is a little bit too much detailed for the specific current kernel Kepler architecture. But the point is, use many threads to hide transfer between global memory and the kernel and the thread. But there is a balance between many threads, okay, but please not very many threads per block, because otherwise, if your block has got too many threads, you may exhaust specific resources inside your module, inside your SM. So typically, at the end of the day, you choose a multiple of 32 within this kind of range, and then you play around with the number of blocks according to the size of your problem. So you can. Those are the main rule of thumb. Okay, other details. Everything is IEEE compliant, but on the other hand, if you don't really need IEEE compliant, you may want to use specialized functions just for GPUs, which are faster but not IEEE compliant. So you can play with this for best performances, very specialized fast performances. Also some other things like it's better bit shift rather than modulo, but this is also true for processors, for the normal CPUs. And the other point to be considered is that again it's something for optimization. So maybe we can have in the afternoon a little bit. Since a warp it's a group of threads launching all together. Clearly, if you don't want to have branches inside the same warp. Otherwise, you lose performances. Simply because some portion of the warp it's doing something, then you have to wait, and some other portion is doing something, because it's inside the warp it's a SIMD. Everything must be in step. But again, we can do that in the afternoon. A few words about compilation. For example, on Linux, in practice, you have a standard compiler, for example, G++, providing object code. The CUDA compiler and VCC inside your CUDA toolkit is able to split this. The single code is able to split it between host executable and CUDA kernels. So the host executable is then given to some provided host compiler, for example GCC again, giving some object code for the host. The CUDA kernels are actually compiled first in an intermediate language called PTX. PTX, it's like a Java kind of generic model for, it's a sort of high-level assembler for GPUs. You don't need to have a look at that, but just to know, PTX it's something not related to a specific GPU hardware, like Java. So it's an intermediate byte code, so to speak. Then this is further compiled into specific hardware assembler, basically, or object code, if you like. Then, of course, the loader, at the end of the day, the loader available inside the toolkit is able to put all together and give you a single executable file. Very similar in Visual Studio, actually. So basically, you have a DLL. Visual Studio is able to produce a DLL when you have it with your CUDA compiler. Commands, okay, the standard commands. Typically, you use .cu for CUDA-related files like kernels, and also maybe host code where you have the kernel launches. You need to typically you need to put them on .cu. Otherwise, it can be tricky for your file or whatever to select the proper compiler. And the other options are typical for standard options. So this completes the general introduction to the CUDA model. In the afternoon, we will see whether we can maybe try to resume the hands-on or not. But in any case, in the afternoon, we have lots of other topics to cover, including OpenACC, optimization, and so on. So we can
now
still,
we have 20 minutes.
Yeah.
If you
So I think that in order to have a nice split, I wonder if it's a problem if we start lunch earlier than expected.
lunch must be in hour. Lunch it's
I mean, it's a problem for
lunch
the
is
restaurant.
20 minutes and we must lunch in hour because not the hotel people, right? Going to lunch
Yeah, sure.
after.
Okay.
Now,
If you think,
think
because otherwise
we can do lunch now.
now I think it's
Now
better now.
I'm going to ask, okay? And if you prefer,
Yeah, I think it's better because I can, in the meanwhile, I can also ask my US colleague what happened
Okay.
to the quick lab and so on.
okay, I'm going to
Okay.
ask you also
Yeah.
first. Okay. Okay.
Yeah.
I'm going to try the lunch now. Okay. Now I'm going to launch. Okay. And this event has transmitted in live via YouTube, right? This message is for the YouTube people. Thank you very much for following us. And now the people follow us through YouTube. Okay, you can see in the future this video in on web, right? And now it's all for us. Thank you very much.
I have no comment.